Right, hello everybody. Okay, um, what I thought of doing today is focusing on shapes of molecules and polarity of molecules. So you do need to know how to do Lewis diagrams or Lewis structures for this. Do you know what I mean when I say a Lewis structure? Yep. Okay, great. And as I say, if you don't know, don't let yourself be sidelined because I'd rather make sure that you know how to do it. Okay, well, if you know how to do a loose structure, you always start with that when you want to work out shapes of molecules. So if I follow this pattern, and I hope you can all see this, if you follow this pattern, you shouldn't have a problem with shapes. Now, I'm focusing on those sort of types of questions that go to merit and excellence. So Lewis diagrams are pretty much an achieved level question, but going on to explaining shapes and explaining polarity is a merit and excellence level question. So first of all, you do need some off-by-heart learning of shapes. Now you learn some at level 2, like tetrahedral, trigonal, pyramidal. Is there any other one you can remember from last year? If you can't remember, just say, nope, I know it was a year ago. No. Okay, so there are 5 basic shapes. Now, you learned just a few of them last year at level 2. So now you're extending it to the 5 basic shapes. And then this year you also do all the variations on those shapes. And we'll go through them, so don't worry about that. But that's the first step you need to do. So make yourself flashcards. If you want to do a Quizlet, when I say Quizlet, do you know what I mean by that? Has anybody played around with Quizlets? Okay, some of you have, some you haven't. Okay, if you just Google Quizlet, then you can just play a game. I'm going to actually just get out of here, and I'll actually, because you can, this is going slightly off track. But for instance, if you wanted to learn anions and cations, so here's the level 2 ones with flashcards. You can learn it as like this, or you can play games where you make everything disappear, start your game. So an oxide you have to match with O2. Now this is probably too small for you to see, but they're sort of ways of doing learning off by heart those basic facts that you need to know. And this is one example. So if you want me to set up something like this, you could even set up yourself, but I can easily set it up, and then you can just play those games to learn. So just give me an email or your teacher an email, and then we can do it. Okay, yeah, because you do need to know those basic facts. Right, I'm just going to go. Sorry. There. Okay. The next thing you need to do when you want to learn shapes is work out the total number of regions of negative charge. So this is pairs of electrons, either bonding pairs of electrons and non-bonding pairs of electrons. So you count up all those pairs, and that'll give you the number of regions of negative charge. Because what do you know about negative charges? Do they repel each other or attract each other? Repel. So if you've got 2 regions of negative charge, they're going to repel each other as much as possible. So the biggest way they can repel each other, or the furthest apart they can be from each other, is if there is 180 degrees between them. So one's on this side and the other one's on that side. If there were 3 areas of negative charge, the most they can repel each other is 120 degrees. Because if you look at 3-dimensional space, it'll still be something that's planar with 120 degrees between them. If you've got 4 regions of negative charge, then you get something that's a tetrahedral shape, and that's 109 degrees. Now, you will get to know and be able to spout it out like I'm doing now, but it does come with practice. So you do need to count the number of negative charge, and then you apply the shape. So you look at the bonding pairs, the non-bonding pairs, work out the electron geometry, and then the molecular geometry. So let's do some examples, and I'm just going to get out of here and go to this. This is a FET animation or simulation. If you just Google FET shapes, then you will get the simulation, and it should run on all computers because it's HTML. So it should run on Mac, it should run on your Microsoft, and so on. So here's an example of a molecular shape that's just got two bonds to it. So it's got two areas of negative charge. Now can you see, I know it's a little bit on the small side. I'll see if I can make it. No, it doesn't zoom in, I'm afraid. Can you see this molecular geometry on this side and electron geometry on that side? Yep, great. Okay, so remember that you've got to talk about both when you're explaining shape. So if I've got, and I'll just tick those so you can see, if I've got two areas of negative charge, so this is one area over here and this is one area over there, it's linear, both the electron geometry as well as the molecular geometry. This molecule is a linear shape. Okay, if I added another bond to it, I've now got three areas of negative charge. So they're going to repel each other to the maximum amount. So it's a trigonal planar. And because I don't have any lone pairs of electrons, non-bonding pairs of electrons, notice that the molecular geometry is the same as the electron geometry. Okay, because every bond, or every area of negative charge is a bond. If I add another bond, okay, there's my tetrahedral shape, and you can drag this around as you like. Notice bonds are flexible, you know, they can go up and down. Okay, so that's your tetrahedral shape, and the bond angle between any two bonds is 109 degrees. It's one of those things you do have to learn. So for the when I had a trigonal planar, it's 120, and you can actually show bond angles. So if I went back to there and I just added bonds, okay, that's obviously linear because two atoms have to be linear, there can't be anything else. Okay, three atoms, if there are no non-bonding pairs, will also be linear, 180 degrees, trigonal planar. And notice the bond angles can change as you move them, but it'll always go back to 120 when it settles down. And then the tetrahedral is 109.5, and I can carry on to 5. Now, this one is perhaps the tricky one to visualize, and this is where the simulation is really good if you try it yourself. Do you notice there are two bonds that are directly opposite each other at 180 degrees to each other? And then there's this middle bit here, if I just sort of turn it round and round, that is a different angle. Let me make it, I want you to see, there you go. Okay, so now we're looking end on to those two bonds that are directly opposite each other. And can you see I've now got three bonds that's like a trigonal planar part, 120 degrees from each other. Now this is what we call the trigonal bipyramidal. So I think it's sort of easy to remember. You've got the trigonal planar, which is just the three bonds. And the trigonal bipyramidal is, think of the trigonal planar with one thing going behind and one thing coming out in front. So think of like two pyramids stacked on each other, you know, with the peaks on either end, and that's where the bi comes from, two. So you've got two pyramids, and the pyramid angles from this. So I hope that makes it easier to remember this trigonal bipyramidal. But why this one is more complicated than the others is they've got different bond angles. I mean, the trigonal planar was all 120, regardless of which bond. The tetrahedral was all 109.5, regardless of which bonds. Here, you've got two different bond angles. You've got 120 in this, what we call the equatorial plane. Okay? So those three are maximum from each other at 120 degrees. And then I've got the other one, which is my axial plane. Try and bring it up. Okay. So that's my axial plane, and they are 190, well, it's 180 degrees from one side to the other, but otherwise 90 degrees between bonds. So 90 degrees from this one to that bond, 90 degrees from that one to this one. So you do need to recognize the equatorial axis and the I've gone blank. The vertical axis, okay, or the main axis, the equatorial region and the main region. We could call it the vertical axis. So, do you think you can see those two regions, or those two planes? The axial plane and equatorial plane. Sorry, those are the words I was looking for. So the 120 degrees ones is the equatorial plane, and the axial plane is the straight up-down one. Okay. And as I say, it'll be really good if you played around with it, and then you would really see it. Then the last one you have to know of the 5 basic shapes is the octahedral. And this one is pretty simple because notice all the bond angles are 90 degrees. If I drag this to show the axial plane, notice the equatorial plane is also 90 degrees. So any one of these could actually be an axial plane because everything's 90 degrees. There's no variation between them. So the only tricky one of those 5 basic shapes is the trigonal bipyramidal. Okay. So those are the basic shapes. And you'll notice the electron geometry was the same as the molecular geometry. If I put in some non-bonding electrons, then they start getting different. So I'll go back to my atom again, and if I added a bond, okay, it doesn't matter how many lone pairs I've got, because I've only got 2 atoms, I'm always going to have a linear molecule. So here I'm adding a lone pair, and notice it comes immediately 180 degrees from that, but it's still a linear molecule. Okay, if I add another one, notice the molecule is linear, but the electron geometry is trigonal planar. Now, why would that be? Okay, because there's repulsion. We've got 3 areas of negative charge. That's why I say whenever you have to discuss shapes, you have to first draw the Lewis structure so you know how many bonding and non-bonding electrons there are, and then you go and hone in on how many areas of negative charge, because they're going to repel each other. That'll give you the electron geometry, and then from the electron geometry you can say the molecular geometry, because you can say of those 3 areas of negative charge, 2 are non-bonding pairs and 1's a bonding pair, so it'll be a linear molecule. Okay, yes, and so Johnny and April, and that's all correct. So I can keep on adding lone pairs, and notice it stays a linear molecule, but the electron geometry changes. Okay, so if I go back, and now I have 2 bonding pairs. If I now add my non-bonding pair of electrons, notice the electron geometry is trigonal planar again, because I've got 3 areas of negative charge, all repelling each other as much as possible. But we call the molecule bent, okay, because those 2 bonds are not directly opposite each other, 180 degrees, they have been pushed closer together because of that non-bonding pair of electrons, or that third region of negative charge. So notice this is bent, and if I add another lone pair, notice the molecular geometry is still bent. So this is a favorite question that comes up in the exams. They'll say SO2 is bent and H2O is bent, but one has a bond angle of 120 and the other one has a bond angle of 109. Why? And then you have to explain the first, remember what I said, look at the number of areas of negative charge, work out the electron geometry, and say, well, because of this one, it's 4 areas of negative charge. The electron geometry will be tetrahedral with 109 bond angle between them, because those electrons are repelling each other in all directions. Remember that repulsion is in 3D. And so then water, for instance, because this will be like O, H, and H, it'll be bent with a bond angle of 109, whereas the previous example was SO2. And again, you would draw the Lewis structure first to show that there are 3 areas of negative charge. Any questions on that? Can you see the difference between those 2 bent molecules? Yeah. Okay. Right. And I can carry on adding. And notice when I have 3 lone pairs of electrons, it goes back to a linear molecule again, because the lone pairs all add in that equatorial plane. And the reason they do this is a non-bonding or pair of electrons or lone pair of electrons, they only attach to one nucleus, if you like, not shared between 2. And because of that, it can spread out a bit and it repels a bit more, whereas bonding electrons are sort of pulled by 2 nuclei, so they've got a narrower focus, they don't spread out as much. So because these repel a bit more and they spread out a bit more, they try and get maximum repulsion from each other. Now, the simulation won't allow me to do this, but can you imagine if the non-bonding pair came in over here and not over there? So say the bond went like this and then the second bond went like that. What would be the bond angle between these 2 lone pairs? This one that's over here and this imaginary lone pair that's over here. So think of the bond angle between the equatorial plane and the axial. Correct, Joe, it's 90. Now 90 is a smaller or bigger bond angle than 120. Smaller. So it's not going to like going in over here. It doesn't go into the axial positions because they're too close to each other and they're going to repel more. So the lone pairs always go into the equatorial position first before they'll go onto the axial. Okay, and in this case, because we've got 2, they always pack around there, so that's the other case. You know, it doesn't matter which view you take from this one, it'll always be 90 degrees there between the areas of electron density. But of course the bond angle is 120, because remember, bond angle is always between the bonds, not between the non-bonding pairs, between the bonds. Okay, so any questions on when you have 3 atoms and then varying numbers of lone pairs? Can you see how we get the electron geometry and work out the other one, the linear? So it varies between linear to bent, pretty much. Okay, let's do the next one, which we've got 3. Okay, so it's trigonal planar if we don't have any lone pairs. This is the one you learnt last year for ammonia, where you have a lone pair and then an N over there and H over there. And it's the tetrahedral electron geometry, but we call the name trigonal pyramidal. So there's lots of names that are actually quite similar to each other. So spend some time learning these shape names because they can be confusing. Trigonal pyramidal, trigonal planar, trigonal, bipyramidal. It all sounds very similar. So just spend some time learning those off by heart. I mean, that's just memory work, really. Okay, and carrying on, notice how they've gone into the equatorial plane. So there's my axial plane going along there, and if I add another one, it sort of goes in over there. Oh, and sorry, I didn't get the shape. So that's a T-shaped, and let me just quickly, it was 3, I think I said. We were on this one. That's a T-shaped, and yep, the T-shaped, and then you get the octahedral. Okay. So any questions on that series of shapes? You'll notice there are some, just like bent and bent, T-shape and T-shape. You get those regardless. Okay, so we can go now to when we've got 4 bonding pairs, and if we add the lone pairs, then that's a trigonal bipyramidal electron geometry, but we call this shape a seesaw. And I think perhaps the best way to see that is if we have that on top. Can you see these go down and this is on top? And so if you can imagine, this is a seesaw, these can go sort of like up and down sort of thing, and that's your axis. So I don't know if you can picture the seesaw there, but that's what it's called. I think the United States calls this a different shape, but I can't remember offhand what they call it, just in case you come across another name. So see John Lee's typing there. Okay, in case you watch other videos. Right, and then I add, because we've already got 5 there now, if we add the next one, the lump is going around the middle here. Good one. And then there you go. Notice they are opposite each other, and because they're opposite each other, it's because of their bigger repulsion than the bonding pairs. So the lone pair is not going to come in over here where it's 90 degrees. They want to be as far away from each other as possible. So notice that this is a planar molecule again. It's called square planar because there's basically 4 corners, and it's in a plane. You're not going to have 1, 2, and then one perhaps coming down here and one over there. It'll always be planar. And if you asked why, why is it a square planar shape, or why is it planar, and so on, it normally comes in when they say, is this a polar or non-polar molecule? Then you can say your lone pairs will go into the axial plane because they want to repel each other as much as possible. Okay, so those are pretty much the shapes, because we haven't done 5 bonds. So 1, 2, 3, 4, 5. If I now add 1 lone pair, then you get the last shape to learn is the square pyramidal, where this comes in. It doesn't matter which axis it comes in because there's 4 in every plane, if you like. So you could have made it in the axial plane or in the equatorial plane. It doesn't really matter because they're all 90 degrees from each other. Okay, Joe, what does it mean to be polar? We're coming on to that later on in this lesson. Okay, so we'll discuss that. Yep, so it is to do with it's the bonds are when you have a polar bond, it's where the bond is unequally shared. But then we go on to polar molecules. Right, so any question about shapes? Do you think you can, if you know the Lewis structure, work out the areas of negative charge, get the electron geometry, and then work out the molecular geometry based on the number of bonding and non-bonding pairs? Okay, great. So that's but always start off with a number of regions of negative charge. Don't go honing straight on the bonding and say it's got 5 bonding pairs and 2 non-bonding pairs or whatever. Sorry, it's 5 plus 1 is 6, because you don't go more than 6. Just give the total number first, the electron geometry, because that'll tell you the bond angle. And once you've got the bond angle, you can go on to the shape, because you can then say it's got so many non-bonding, so many bonding, so it's this molecular shape. Okay. And so these are the 5 basic shapes. So these are the number of pairs of electrons around the central atom. And so those are the names of the shapes: linear, trigonal, planar, tetrahedral. That's what you learned at level 2. Level 3, you're now adding on the trigonal, bipyramidal, and the octahedral. So I see John Lee's typing, but we'll carry on. This is also in your book. So here we've spread it out a bit more, because we're now doing your basic shapes plus the variations with the bonding and non-bonding pairs. John Lee, why is it octahedral if there are 6 pairs of electrons? Because that actually has got 8 facets around it. So if you think of your octahedral shape and you count the number of planes in that shape, you know, surface planes, all the triangles around it, you'll find there are 8. And that's where the octahedral comes from. Okay, so I don't know if you can see, here's an octahedral. This triangle over here is 1, this triangle over here is 2, 3, 4, and the same thing for below it. Yeah. Okay. It's just the octa, you think of 8, so you think it should be 8 bonds, but it's actually the surfaces, if you like. So again, this is sheer learning work. So make time square, do either Quizlet or flashcards or something, just to help you learn that off by heart. And then, as I say, work out the axial plane and the equatorial plane. It starts becoming important from down here. Trigonal, bipyramidal, this one. Notice how they're always adding into the equatorial plane. And we've done the same thing here, but I will say it's because they're all 90 degrees from each other, it's not actually that important. Okay, so you think you can all discuss shapes of molecules without a problem? Okay, now here I've got, just as I had those simulations last week with the electron configurations and so on, in OTL there's also a simulation where you go through these steps to work out the molecular shape. So go into OTL, click on those links, and you can practice on that yourself. Okay, now what I've got here is just quickly some examples. Now, if you've got the booklet CH3042 in front of you, you can turn to the page of shapes, otherwise we'll just see how much you remember. So remember, if we're looking at shapes, you first look at the areas of negative charge. So this one, which is like carbon dioxide, how many areas of negative charge? Okay, April, you've said 4. If you're looking at regions, not how many electrons in total, but how many areas of negative charge. So it's got, and it's a good point you raised that, April. I'm glad you did that, because I never said that in my lesson so far. Double bonds and triple bonds still count as a single area of negative charge. So thank you for raising that, April. Because those electrons are localized in that area. So it's got 2 areas, 1, 2 of negative charge, and so its electron geometry is going to be linear, and its molecular geometry will be linear. Okay, and now, Joe, you've got, is it planar? Yes, it'll be planar. Okay, it won't be trigonal planar, but it's still going to be a plane. It's not going to be at a right angle, because the bond angles will be 180 degrees. So it'll be flat. Right, how about this one? So first of all, the electron geometry. Does anybody remember what the electron geometry would be? So you've got to count the, okay, there are 5 areas of negative charge, good. So what do we call them? Trigonal bipyramidal, good. Okay. Now we just look at the molecule, and I think it's easy enough to see that although the electron geometry is trigonal bipyramidal, the molecule is actually linear because all those lone pairs have gone into the equatorial plane. Okay, great there. So this is an example of xenon difluoride. I know a lot of students ask me, they say, xenon, that's a noble gas. How on earth can it form bonds? The bigger atoms near the bottom of the periodic table can be forced to do various things because they've got so many electrons available. So xenon, under high pressures and temperatures, will react with very electronegative elements. And by that, I pretty much mean fluorine and oxygen. It won't actually react with anything else. So you can get compounds of xenon, which is a group 18 noble gas, xenon trioxide, xenon difluoride, and so on. So it's just one of those things that people played around with to see if they could make molecules out of noble gases. And as I say, the shape, molecular shape is linear, but the electron geometry, which I've done in blue, is trigonal bipyramidal. Let's have a look at this one. Okay, what is the electron geometry? Trigonal bipyramidal. Good. Okay, so what now do we call the molecular geometry? Because we've got one lone pair there. Does anybody remember? John Lee had a joke about it, about the kid in the middle. I don't know if you remember that. Seesaw, correct, yes. So that'll be the sorry, I've gone down that way. Okay, that is a seesaw. If we go back to here, I think I was just trying to show 3 things in a row. So 1, 2, 3, 1, 2, 3. Here I've still got 3, and there I've got 3. So we're just trying to show the different ones. And here's that SO2 I was talking about compared to H2O. So that is a favorite question. And then here are other examples with a trigonal bipyramidal electron geometry, but the shape of the molecule differs. That one's linear, that one's seesaw, and that one's a T-shape, just because of the different numbers of lone pairs. Okay, right, so as I say, it's a lot to take in, and I don't expect you to spout all these shapes right now, but because I do see time going, practice whenever you can, just to make sure that you know these. So this one is an electron geometry of octahedral, and this shape is what? The molecular shape. So quite a square planar, correct. Okay, and this one is from level 2, so hopefully you know it, and there's no lone pairs there either. So that one, hopefully you all know, is trigonal planar. Here is one where it's an octahedral electron geometry, because there are 6 areas of negative charge here, and yep, so this, well, that one's square planar, that one's trigonal planar, as I said. Oh, I've forgotten which way I'd done these things. You know the ammonia one, of course, from last year. So this one's the square pyramid and not square planar. So I've put these here because it can be confusing. The words square planar, square pyramid, trigonal planar, trigonal pyramidal. So just make sure you don't confuse those very similar sounding names. Any questions? Nope? Okay. Right. So somebody, I think it was Joe or April, I can't quite remember, was asking about polarity. We use the term polarity or polar pretty much based on magnets. You know, the North Pole and the South Pole on the Earth, there's a pole between them, okay. But instead of a magnetic distribution, well, we also have a magnetic distribution a bit over here. is we've got an uneven distribution of electrons. And because there's an uneven distribution, it's going to affect the properties of the molecule, because one end will be more negative and the other one will be more positive, so it'll attract things more or less strongly depending on how that distribution is of electrons is around the molecule. So that's where the word polar comes from. Just think of it's like a pole, and can you see this yellow arrow over here? Yep. Okay, great. So this is what we call a molecular dipole. Now, a dipole is just a fancy word for saying a separation of charge. It's measured in debye units in case you come across it in physics. It's got vector properties if you've done that in physics. I'm just mentioning this in case you have got that physics background, and it just makes it then easier to think of it in chemistry. But it's the overall separation of charge. Okay, so you've done the things in physics, Joe and Johnny, right? So how do I know what this separation of charge is going to be like? It's all to do with electronegativity. Now remember when we did trends in electronegativity? Do you remember what that was? So, okay, while Joe was typing, just think of what it is. Sorry, I thought I was going on to the next slide and I've forgotten I put this one in. Okay, so John needs to, okay, no. Okay, remember electronegativity is the attraction an atom has, so it's a property of an atom, or, of an element. Attraction has onto its bonding electrons. Okay, so an atom wants to hold on to its atoms, not quite, you were typing too fast there, Johnny. Atoms are holding on to its bonding electrons. So in that previous slide, if I can go last viewed, okay, hydrogen and fluorine are sharing electrons in that bond, but fluorine has got a much stronger attraction. And think of those periodic trends where hydrogen sits, it's only got one proton and one electron close by, but fluorine has got 9 protons, so its nuclear charge is so much greater, and its valence electrons are on the second energy level, not that much further away, not that much more shielding, so it's a very, very strong attraction. Fluorine is actually quite a small molecule, quite a small atom, so it holds onto its electrons very strongly. It's the most electronegative element. Hydrogen, not that electronegative, so of course those electrons, instead of being shared equally, go more to the fluorine and hardly anything to the hydrogen. Fluorine is given a value that somebody thought up, the Pauling scale of 4. Hydrogen is given a value of 2.1. So you can see fluorine has got a much bigger attraction. And so the dipole is always in the direction of the negative charge. This is very much the negative end of the molecule, and that's the positive end. So to work out the polarity, you just follow these steps. You draw the Lewis structure, because you need to know the shape of the molecule to be able to explain polarity. And to work out the shape, you need to know the number of negative charge, negative areas, or areas of negative charge. And to know that, you need to know the Lewis structure. So you have to go all the way back to the Lewis structure. Then you count up the total number of regions of negative charge or electron density, same thing. That'll give you the electron geometry. You need to know that because you need to work out the molecular shape. This is very important. And then you work out, is there a difference in electronegativity and the bonding atoms? So with H and F, there was a difference. But if I had F and F as an F2, there is no difference in electronegativity. So there would be sharing of electrons, equal sharing there. So if there's equal sharing, there's no bond dipole, because they are, remember, dipole is just a fancy word for separation of charge. So if there's equal sharing in the bond, there's no separation of charge. Everything is equal. If there's an unequal sharing, then there is a bond dipole present. So like fluorine grabbing the electrons more than hydrogen. Okay, then the final step, and we'll do lots of examples, is to see if the bond dipoles cancel or not. And if they cancel, because the molecule is totally symmetrical both in shape and atoms, then there's no molecular dipole. If the bond dipoles don't cancel, because the molecule is not symmetrical, either in shape or atoms or both, then there will be a molecular dipole, like that yellow arrow you saw in HF. So that's a lot to take in, so let's do some examples. You are not expected to know the individual values for electronegativity. You know, I spouted forth just now, fluorine is 4 and hydrogen is 2.1. We don't expect you to know that, but we do expect you to know the trends. So if I've got H together with O, for instance, O will be more electronegative than H because we're increasing in electronegativity across the period. Okay, or if I've got F combined with S, okay, F would be more electronegative than S. So we do expect you to know those sort of things. Okay, so fluorine is the most electronegative, so that's the easiest one to remember. Okay, and then you've got your HF. Now, this, don't worry about this. I've got it in your book about the unequal sharing. The more unequal it is, the more ionic it becomes. Okay, Joe, you had a question there. Atomic radius, is that for the nucleus of the whole atom? What? Yep, atomic radius is not just for the nucleus, it's for the whole atom. You must probably, oh yeah, so it's not just the nucleus, because the nucleus is actually very, very tiny. It's like a cricket ball in the whole big, enormous stadium. So we're talking about like the whole stadium as being the size of the atom, and the radius would be from the center of the stadium to the outside. Okay, right, so usually we say around about 1.7 it becomes ionic, but there are some things like BF3 that is actually molecular and it's still got a difference of 2. So around about 1.72 it sort of changes and then it becomes ionic. So cesium fluoride, cesium, remember, is down here in the periodic table, fluoride is up there in the periodic table, so there's a big difference in electronegativity. That will have the biggest polarity, separation of charge, so we consider that definitely ionic. Okay, right, so that's just to get you an idea of there's a continuum. It's not that this one's definitely covalent and this one's, you know, polar covalent and that's ionic. It's sort of varying degrees as we go through. Okay, right. And then, as I say, that's what the electronegativity is. Now, this is an example we're going to use now in terms of another FET animation. So if you just Google FET polarity, you should get this. So we're going to go through this now. Okay. So I hope that's sort of clear enough. Unfortunately, I can't make this bigger. Can you see this clearly? Okay, right. And as I say, please go in. The links are on OTL and have a play. This one is Java based, not HTML. So I know Apple doesn't like Java, and if you've got very high security settings on your computer that prohibits the use of Java, then you won't be able to do this one either. Okay, but what we're looking at here, it's this arrow here is showing the bond dipole, the separation in charge, always going from positive to negative. So they've made here atom A not very electronegative, so it's not holding onto its electrons very strongly, and atom B is a bit more. And as I move it to making it more and more electronegative, notice how the size of that dipole gets bigger and bigger. Okay, it's getting more and more stronger separation of charge. So this one is becoming more and more positive end on this side, and this one's becoming more and more negative end. And if I make them both the same, notice there's no difference. We've now got something that's non-polar. There's no separation of charge. There's no pole, so it's non-polar. Okay, I can click on partial charge, or let me click on bond character so that you can see it's more covalent. And if I change it, you can see how it's going from more covalent through to polar covalent through to ionic. Okay, so that's just an idea of how this changes. Now, 2 atoms is fairly straightforward, so we're going to go to 3 atoms. So what I've done is I've made it a shape that is non-symmetrical, or the English term is asymmetric. Non-symmetric, I will accept, but please, that's, I think, Americanization. They don't know English terms like asymmetric. So please remember that the real term is asymmetric. And it's 1 S and 2 M's when you spell asymmetric. I remember when I was at university, the lecturer saying, if you spell it ASS, you're making an ass of yourself. So that's the way I always remember that asymmetric has only 1 S in it and 2 M's. Okay, right, so it's asymmetric. Joey with a Y, so ASY. Yep, thanks, Caleb. Right, okay. And this is because to show the separation of charge. So if I made them all the same, so slightly. Okay, you'll notice if the electronegativity is all the same, there is no separation of charge anyway. Okay, so this is a non-polar molecule. Assuming, well, there are lone pairs, which will, when you do ozone, you'll find actually this does become a polar molecule, because remember I said it's non-polar only if the shape, either both the shape and the number of atoms must be the same, okay, or symmetrical. So here the shape is actually asymmetric, so it can never be non-polar. So if I change this and I make B more, can you see, and I put in the partial charges, can you see this is becoming more positive and this is becoming a more negative end? So I can show the bond dipoles, showing that electron distribution is going to the B molecule. Okay. If I reverse it, can you see that now becomes positive and this becomes the negative end? Okay, and you can change, if you've done vectors, you can actually see how things move. You know, if this one now becomes more electronegative, you can see how it changes there. That's not important, that's just a fun thing to do. You won't really have to know that. But as long as you can see that the bond dipoles will add up to give the molecular dipole. So if they're directly opposite each other, they will cancel out. If they're going more or less in the same direction, you're going to have the molecular dipole going in that direction as well. What happens when B is more electronegative than A, but C is more electronegative than B? So we'll make A there, and we'll make B there, and we'll make C there. Okay, you get something like that. So they're vectors. You do not have to do vector calculations in chemistry, so don't worry about that. And you would not have to be able to draw where the molecular dipole is. You must just simply recognize that there would be a molecular dipole. That's all what you would have to do. You wouldn't have to say, oh, this is the negative end, or something like that. Right, so let's do the real molecules, because I think it's easiest if we do this. And I'm going to show the electron density. Well, let's actually do that one because it's a nice color. So here's this HF that we did. And if I show the bond dipole, I don't know if you can see it in gray. And I'm going to show the molecular dipole. So you can see this is the negative end and that's the positive end. And if I go through it, nitrogen, there is no bond dipole at all, because there's equal sharing. And the same thing for oxygen, equal sharing. So those are all non-polar, no molecular dipole. If I go to water, can you see hydrogen is less electronegative than oxygen? So those arrows are pointing towards oxygen, giving me a molecular dipole. So if I have bond dipoles that do not cancel out because of the shape of the molecule being asymmetric, I'm going to have a molecular dipole. And that means I'm going to have a polar molecule. So you can play around with that quite a bit. What I want to do now is go back to my slideshow, because I've got a few examples there. And I just want to go through these steps. So the steps are always the Lewis structure, and it's normally given in an exam, because they normally give you something that's weird, but if you've got the Lewis structure there, you'll be able to work it out. Then you look at the electron geometry, then the molecular shape, okay, because you want to know, is that shape symmetrical or not? Remember, try and see it in 3 dimensions. So water may look symmetrical if you cut it in half vertically, but of course it's not the same at the bottom as on the top, so it's not symmetrical. Then you look at electronegativity differences between all the bonding atoms, particularly in bonding to the central atom, because that'll tell you if there's a bond dipole. So if there's a difference in electronegativity, there'll be a separation in charge in the bond. And then you've got to work out, will those bond dipoles cancel out or not? And that depends all on whether your molecule is symmetrical in terms of atoms and shape. And then if it is totally symmetrical, it'll have no molecular dipole, so it'll be nonpolar. If it is not symmetrical in bonds or atoms, those dipoles will not cancel out. And so it'll be a polar molecule. And as I say, there are some things you can have a look at there. So here's an example of O2. First the Lewis structure, then you work out the geometry. Both atoms have the same electronegativity, so there are no bond dipoles, okay, and it's a symmetrical molecule, so it is a non-polar molecule. Okay, so that's quite a sort of simple one. Here's HCN. So you start off with the Lewis structure, and as I say, it would be given. You work out the electron geometry. It's always around the central atom, so it'll be carbon there. I've only got 2 areas of electron density, so it's linear. The molecular shape is linear, but it's not a symmetrical molecule. Well, let's go down to the electronegativity. You should know from the periodic table that nitrogen is to the right, so nitrogen is more electronegative than carbon. Hopefully you remember that. You are given a periodic table if you can't quite remember, so just have a look at that. And so there is a trend that this one is more electronegative than this one than that. And so there will be a bond dipole in both the CH bond as well as the CN bond, making this very electronegative, or very electron dense or more negative. Okay, try and use your terminology correctly. Like I said, making this area more electronegative, that is not a correct use of electronegative. Remember, electronegative is a property of an atom, of how strongly it holds its bonding electrons. It's not to do with how negative an area is. So because this is more electronegative, this area becomes more negative. So just use your wording carefully. Okay, and this area is more positive, and I've got a bond dipole going all the way through. Sorry, I had to chop it off to try and fit in. And it's an asymmetric molecule because although I can chop it in half like this, and this top half looks the same as this bottom half, if I chop it vertically, the H is not the same as the N. So it's asymmetric, and so the bond dipoles do not cancel out. Please don't say the bonds don't cancel out. Okay, it's not the bonds, it's the separation of charge, not the sharing of electrons that cancel out. It's the separation of charge. So make sure you say the bond dipoles do not cancel out. Okay, here's one with formaldehyde, okay, or methanol. So that's Lewis structure, and 3 areas of negative charge around the central atom, 1, 2, 3. So the electron geometry is trigonal planar and the molecular shape is trigonal planar. There's a difference in electronegativity. Thinking of your periodic table, oxygen is to the right of carbon, so it's more electronegative, which is more electronegative than hydrogen. So there will be a bond dipole, okay, and is that molecule symmetrical? No. Okay, you can see that quite clearly. Although I might cut it in half like this, and this side looks the same as that side, if I cut it in half like this bottom half is nothing like that one up there. So it's an asymmetrical molecule because the atoms are different, and so there is a molecular dipole because there's no cancelling out of the bond dipoles, and that means the molecule's polar. Okay, so here's one BRF5. Okay, so you might go, oh, BRF5, but if you just work through your Lewis structures, you'd be able to work it out. And as I say, for this type of question, they always give it to you in the first place. They always give you the Lewis structure. It's got 8 areas of negative charge because there's a lone pair and 5, sorry, it's got 6 areas of negative charge because it's got a lone pair and 5 bonds. And so it's octahedral, but it's a square pyramidal molecular shape because of that lone pair of electrons. F is more electronegative than bromine. Okay. Yep, you no, not quite seesaw. Seesaw's only got the 4. Okay. And but don't worry, I don't expect you to have learned them all in one lesson. It's a lot to learn. And so if we had a look at this one, you'll see that this bottom area here is more electropositive, and sorry, I'm using that word badly again. This bottom area here is more positive. Do not use the word electropositive when you mean just an area of negative charge. So this is more positive. This area around here is more negative. So for symmetry, yep. So April, good question. For symmetry, basically the best way is to cut along a bond. So if you just cut along this bond, is this side in front of that line the same as behind it? Or if I cut along this bond down here, then is this side equal to that? Now you'll notice if I cut down here, this side is equal to that side, but you've got to do it for all the bonds. So if I do it along this axis here, then this part down here is not the same as over there. So just cut along any bond, and that'll be the best way. Or you could bisect the bonds. I mean, there are a number of different ways you could do it. So Caleb, if the charge on both hydrogen and H2 are equal, the O, will it be symmetric? You mean the electronegativity? There won't be any bond dipoles, but the molecule still won't be symmetrical because the atoms are different. So the bonds will still be the bonds will be nonpolar, but you can still get, because of the shape being not symmetrical, something that's polar. And ozone is an example. And I see it's 4 o'clock, actually, that came up there. So if I just do that, and there was one here, here's a negative anion. So you can get an anion that is totally symmetrical. So the anion is actually nonpolar. Okay? So it may be all totally negative on the outside because it's got a negative charge, but it is considered nonpolar because there's an even distribution of electron density around that central atom. Okay, and I think that's pretty okay. This is ozone. This is the one that's tricky. That'll come up. So just quickly do this one. Ozone, can you see I've got 3 oxygen atoms? So would you expect there to be a bond dipole between these oxygen atoms? No, because it's the same electronegativity. So ozone tends to also come up a bit because, you know, it's like a trick question. You know, people will say, oh, it's polar, because they know they've learnt off by heart it's polar. And then they'll say something about there's a bond dipole because of the difference in electronegativity. And of course, there's no difference in electronegativity. And it's because it's a bent molecule, Caleb, correct. So they have the same electronegativity, but they share the electrons differently. Okay, so that central, now this is where NCEA does let you down a bit, because we don't do resonance where you see all the possibilities and you take then the average. But there are different ways you can draw this, and with the average, the central atom actually has less electron density on it than the outer atoms. And I think you can sort of see this in this molecule. This one's got 1, 2, 4, 6 lone pairs around it. This one's got 2 lone pairs around it compared to only that one, because the bonding pairs are sort of pulled in position there. So the outer ones are actually a bit more electron rich than the inner one, and so because of the asymmetric molecule, those bond dipoles that are caused by an uneven distribution rather than a uneven sharing in a bond, it's an uneven distribution of lone pairs rather than the bond. And so the ozone is polar. Okay, so we'll stop there because we've already gone longer. Any questions? So if you follow those steps in detail like that, you will not have a problem. Okay, you explain every step, spell out the obvious, and you should get excellence. Right, so see April and Johnny are typing. So the amount of lone pairs in the outside oxygen don't make any difference. Well, yes, they do, because they actually do sort of give an indication that there's more electron density around the outer ones than the inner one. As I say, this diagram shows it's equal, whereas here you can say, oh, that one's got 3 and that one's got 2. But I could have drawn equally one where the double bond was over here and the single bond was over there. So, as I say, when you get onto university and you continue with chemistry, you do what's called resonance, and that's where you average all the possible variations. Yeah. So bonding electrons repel less than lone electron pairs. Correct, because the bonding electrons are shared between 2 nuclei, so they're limited in space, whereas the lone pairs are only attached to one nucleus, so they can actually spread out more. Okay, right, well, you all have a good day, and keep the work flowing in. Right, okay, bye.